Okay, short and sweet one this time, hopefully. We are looking at the final part of the wave-particle duality subtopic in the light and atoms topic, and so far we've learnt that light behaves like a wave. Then we've learnt that light also behaves like a particle called a photon, and now we are going to learn that particles, things like electrons and any particle for that matter, protons, any particle, also not only behave like a particle, which seems common sense, but also will behave like a wave. Let's get into it. So, before we go any further, if you haven't already, please make sure you watch this video. It's a TED Ed video. I think it only goes for about 4 or 5 minutes. It's quite a short one, which I think gives a really good introduction to particles and waves, the central mystery of quantum mechanics, which is we're just touching on some quantum mechanics in this part of the course. So, what's going on here? So, firstly, we're familiar with the double slit experiment where we shine light through and we get the interference pattern with constructive and destructive interference. And we talked about also in the previous slide on photons that even if you do this with very low intensity light, you see this form as a series of dots rather than just this continual appearance which you might expect from the wave model of light. And if you repeat that double slit experiment with a beam of electrons and much narrower spaced slits, because we'll talk about why that is the case in a minute, you will see an interference pattern just like with light with electrons. And we're familiar with electrons as particles. They're the small particles that orbit atoms. They have a mass, unlike photons, which don't have a mass. So this seemed a little bit counterintuitive to the scientists of the time. This wasn't the only experiment that was done. Two scientists by the name of Davison and Germer also did an experiment based on here, where they got electrons, heated filament again to generate electrons. We've seen that in like the X-ray. Put those electrons through some accelerating voltages. They also use these to focus the beams with magnetic fields. We won't talk too much about that. And they fired electrons at the surface of a nickel crystal. And that nickel crystal, because of the evenly spaced atoms, acts like a transmission diffraction grating. But instead of transmission, you also get reflection. We don't need to know the detail of that, but just like you can get an interference pattern when you shine light through a transmission diffraction grating, you can also get an interference pattern in the reflected light. And when they did that, they observed, so fired the electrons at this nickel crystal, then they had a detector that picked up the electrons that were reflected and they moved that around at various angles, and they picked up a diffraction pattern like this, where you saw areas of high and low intensity of electrons striking the detector, just in the same way that you would see if this light had passed through and produced a diffraction pattern on the other side, like we saw when we shined a laser light through a transmission diffraction grating. So, based on simple optics, you would expect that the angle of the incident electron beam would equal the angle of the reflected beam, and we wouldn't expect to see this sort of diffraction pattern forming. So this was again further evidence that electrons were behaving like a wave. And sorry, I should have added here, not only did they see this pattern, when they worked it out using d sine theta equals m lambda, they worked out that the areas of constructive and destructive interference of the electron beam corresponded to the d sine theta equals m lambda, so the transmission grating equation. So it was showing that this was basically behaving like, these electrons were behaving like a wave and obeying that sort of rule, if you like, for the constructive and destructive interference in from a transmission or from a diffraction grating. So this was further evidence that particles, i.e. electrons, were also behaving like waves, not just like particles. And if you worked out the wavelength of these particles, firstly using the d sine theta equals m lambda equation, and then using the relationship that we use for photons, which we now call, we call this for particles the de Broglie wavelength, so the de Broglie relationship. So you can work out the wavelength again here using this formula. The two wavelengths worked out using those two different methods coincided with each other. So that supported that we had two sorts of evidence that showed that the particles were behaving like waves, and in terms of the wavelength of those waves, those gave the same value. So, how are we going? We can describe the two-slit interference pattern with electrons. We can describe, hopefully now, the Davison-Germer experiment and what was observed. We can compare the de Broglie wavelength, the ones worked out using this calculation, with the wavelength required to produce the observations of the Davison-Germer experiment and in two-slit interference patterns. So particularly here, the d sine theta equals m lambda. So compare those and see if they coincide, which would be evidence that both experiments are, or both bits of information are telling you that it has the same wavelength. The other thing you have to do, which I think is pretty straightforward and similar to what we did earlier on with photons, is solve problems involving the use of the formula lambda equals h over p for electrons and other particles. So if we want to work out the wavelength of a particle, the wavelength is equal to h divided by p. H is Planck's constant, which we've talked about before. P is the momentum. Now, often you might not be given the momentum, so you might need to work out the momentum from knowing the mass and the velocity of the particle. So it might just tell you its velocity, and we know the mass of all those fundamental particles, so we can work out the momentum. And sometimes, if they want to be really difficult, they might just tell you what the energy of the particle is. And we know that energy equals a half mv squared. So we can rearrange that formula there and get the velocity. And then once we've got the velocity, we can plug it into that equation there and work out the momentum. So, a little bit tricky, but that should not be beyond Year 12 physics students at this stage of their Year 12 physics student pathway. But that covers everything you need to know about the wave behaviour of particles. Cheers.